So, whenever you have a physics problem, I don't care what grade physics you do, grade 11, grade 12, first year, become an engineer or actually study physics, there are always two types of diagrams that can be sketched for the problem. Okay, here's the good news. One of them, I will never ask you for it. Okay, other teachers might. I will never bother you with. Okay, the other one, either I'm going to explicitly ask for it, or even if you're not asked, there is no other way to do the problem unless you actually do it. So, does anyone remember the first name or the name of the first diagram from grade 11 physics? By the way, today's, like at least this note, is the exact same thing like grade 11. Who remembers the first kind of diagram that I am going to ask you to sketch? Well, I'm usually going to start the sketching with. Yes? Nope, that's the second one. What's the first one? System diagram. Thank you. So, the first one is a system diagram. And the easiest way to understand what a system diagram is that it's your painting of the problem. So think about it this way. Let's say that, for example, you're taking, I know, grade 11 math or grade 12, and you've got yourself a geometry problem where you have to use the sine or the cosine law. The system diagram is your painting of the problem. For example, two planes going away. Just give me a visual of what the problem is. Okay? So that's the first kind of diagram, system. Why is it called system diagram? Because basically you're going to mostly sketch more than one object interacting together. And that's what a system is. A system is a bunch of things affecting each other's existence and behavior. The second one is what Ahmed said, which is the building block of diagrams in what? In physics. Free body diagram, or the infamous FBD. Every time you're going to hear FBD in any science or physics themed course, we're talking about free body diagram. And that one is where the physics really is, because it's the breakdown of all forces in action. All forces in action. Actually, I should say all relevant forces in action, because forces are all around us, but oftentimes some of them are completely irrelevant to whatever situation we're studying. Okay? So breakdown of relevant forces in action. Okay? I will never ask you to sketch a system diagram. Okay? Explicitly, I won't. I will do it all the time, but I will not ask you to do it. Okay? However, when it comes to what? When it comes to a free body diagram, you will either be explicitly asked, which means if you did it without using it, without showing it, you will not get full marks because there will be marks for it. Okay? By the way, in grade 12 and university as well. Or you will have to sketch one anyway to be fully able to understand the problem. And this is a very important word. What is this word? What does decompose mean? Break down or break apart. Exactly, yes. Okay? Really helpful with the what? With the 2D trigonometry work that we've been doing sometimes with vectors. Okay? All right? Good? Okay. Okay, so let's do a system diagram example. So, a typical problem. You are pushing a textbook to the right along the surface of a table. Okay? So you're pushing the textbook to the right along the surface of a table. The first thing you have to identify is or sketch a system diagram of the problem. First thing you have to identify is what objects are mentioned here. Making up the system. Book, textbook. Okay, what else? Your hand or some kind of a pushing agent, and the whole table or just the table surface? Just the table surface, whatever is relevant from the surface, okay? So, the only objects relevant here are textbook, table surface, and finally, pushing factor, which could be a hand. Okay? So really we have just to sketch these three things. Okay, well, here is my way of sketching a textbook is always sketching a box with like leaves or pages through it. And then I'm gonna sketch the table. Don't have to sketch a full table, you can just sketch the surface and a part of the legs, that's all. And then finally, since I am pushing to the right, I am just basically making more space on the left to push or to sketch the hand. Okay? That's it. We're done. Oh, one more thing. Whenever there is motion, please always indicate the direction of motion. Obviously, the direction of motion here is which way? It does say in the problem. to the right. Done. That's it. Full marks. That is full marks for system diagram, which I will never bother you with. Okay? Okay, so let's go to the what? Let's go to the second slide or next slide. Free body diagram. What if I asked you to do this problem, but instead of providing an SD, I asked you to provide an FBD? Here's the thing about free body diagram. I have to tell you an FBD of the what? I have to tell you what object of interest, or actually sketching the FBD of. Technically, you can sketch an FBD of any object in the problem. You can sketch the FBD of the table. You can sketch the FBD of the hand. However, which one is the most interesting object in this problem? The text, because it's the one undergoing motion. That's it. So, by the way, technically, I always have to, but okay, sometimes you can just look at the problem and say, if I just say sketch an FBD of this problem, and I don't say what object, oftentimes you can tell which one is the most interesting thing. I will still make sure I explicitly tell you what. If I don't, please raise your hand for me to actually make an announcement of what the object in the FBD is. Okay, so the only object technically that has to be sketched is the what? Okay, everyone, just so you know, in university, if you're asked for an FBD and you sketch more than one object in the FBD, you get marks off. Because it's called free what? Free body, not bodies. Only how many objects are supposed to be sketched? Just one. However, as anyone who did grade 11 physics with me before, you know that I always sketch what? All the objects, and then I focus on just what? I just focus on one. And my reason is, when you sketch all the objects and you show how they interact with the object of interest, you actually give a reason why every force does exist. However, I remember actually from my second year teaching, back 11 years ago, my students who made it to first year came back and they told me, you cost us some marks. I'm like, why? They were like, because we sketched FBDs the way you showed us in grade 12 physics, and my way was always what? Sketch the whole thing, and then just focusing on one and putting all the forces on. They were like, no, you don't do that. You sketch a single what? A single object, and not just even as an object, as a what? As a point, as a dot, and then you what? You put all the forces on it. So I cost them marks in the first midterm of physics because they sketched my way. So please know, in first year, oftentimes the prof only wants how many objects? Just one. You might end up with a prof who's okay with what? With a system diagram, with just a single object in it. It's completely up to them. All right? So here's my object. Now, let's talk about forces here. What definitely is the first force that have to be acted on this object? Gravity. Gravity. Unless I tell you what? Unless I tell you that this object is in deep space, or for some reason, gravity has been eliminated, you have to sketch gravity. Okay? What direction does gravity always point? Straight down, technically towards the center of the planet. Okay, so gravity due to Earth. All right. Here it is. Done. That's it. By the way, do you need to give me an arrow on top of the F? Did you already show me a direction for the F? Did you already show me the direction of the F? You did. Then you're already telling me it's a vector. You do not need to tell me what F arrow G. I know it's a vector. You just told me that it's pointing down. Done. Okay. What should be my next force? Raise your hand. Josh.
Normal force.
Why normal? What's your justification that there has to be normal force in this problem? There is a table. So, by the way, if there is no surface, what would happen to this book? Just what? Are we told it's falling down? Which means what? There has to be a what? A counter force. Exactly. There has to be a balancing force. Because there's a surface, a flat plane. That's what? That's normal. How does it point in this way? straight up. What was the symbol for normal force? What n do we use? Smaller or capital? Usually we use capital. Good. All right, two forces done. What's my next force? Applied, because are we told of an actual applied force on the object? Yes, we're told it's being pushed, which means explicitly there is something pushing it. All right, which way is it pushing it though? Right. To the right, which means, okay, everyone, just so you know, here's the difference between engineering courses and physics courses. In an engineering course, just so you know, you have to, and some of you will actually remember this because you will go to first year engineering and you will take a course called statics. Statics. Statics means everything that doesn't move. Okay, static structures. Okay, in a statics course, wherever you're pushing, you have to put the force going in. So, for example, how do you push a boat? Do you push it from this side or this side? If you're gonna push it that way, you're pushing this side like this, right? So in first year engineering, in the statics course, you have got to make the force go into the object. Okay, that's for engineering. But for physics, forces always go in or come out of the object. In a physics analysis, in an FBD analysis, you always make the forces come into the object or out of the object. Out of the object, which means even if it's actually pushing it physically on this side of the boat, you trace its effect, and then you make it go this way. Okay? Forces always come out of of the center of mass of the object. Done. All right. What symbol do we use for force applied? I mean, there are so many. FA, FAPP, FBook. Sorry, not FBook. F hand or whatever. Okay. So, yep. FAPP. I chose the lowercase for app. You could have done uppercase. Doesn't matter. Okay. One more force. Amar. Are you told anything about friction being negligible or about this the surface of the table being super smooth? Unless you're told that, you always have to account for what? Or to account for the existence of it, which means it has to exist. Which way does friction always go? With you or against you? Never goes with you, it always goes against. Friction never pushes you forward. It always pulls you or brings you backward. It always resists motion, not supplies or supports motion. So that means it has to go this way. By the way, does friction really act on the center of mass of the object or on the surface of interaction? Yet, where are we going to sketch it? We are going to sketch it from here. Okay? All right. What was the symbol for force of friction? The easiest one. F. With what? FF. F uppercase, F lowercase for the subscript. Done. What's the only thing missing so far? Just one more thing. One more thing that we still did in the first diagram. The what? The motion direction. Always put the motion direction just like you did with kinematics. Because you know we're going to choose some positive and negative direction at some point. Done. That's it. Don't worry about positive minus now. We're going to do more analysis tomorrow. Okay? That's it. That's an FBD. That is an FBD. But again, in first year, someone might actually take box off because you sketched a what still? You still sketched an object. You should only sketch a what? A thick dot, assuming that the entire object has been compressed to what? To one small point. Okay? I did not make the rules. I was born into them just like you are. Okay? Just making sure that you know it for the next day. Okay? All right. By the way, just so you know, anyone here taking calculus, when Mr. Shivers starts vectors with you, so in vectors, you are going to do a lot of force analysis, and it will be amazing because it will be done, it will be usually after we're done what? Forces for this course. And you will have seen 10 times what you see in calculus and vectors in this course. Okay? And you will see that he's going to do it the exact same way with you. You have to make everything come out of the center of mass of the object with a thick dot. Okay? All right. Let's compare both. Okay? Let's compare the features of both. Okay. So what's, for example, the first feature of SD versus FBD? In an SD, you are allowed to sketch what? But in an FBD, technically, you only sketch how many? One, which is the object of interest. Okay. Single object. Again, it's called a free body, not a free bodies diagram. Okay. All right. What's another distinction? Well, in an SD, you do not show any forces. Because remember, everyone, a force is what we call an invisible effect. You know it's there, you don't see it, but you judge it by its effect. You judge it by its effect. I push on this pencil case. I don't see a force, but I do see the motion happening as the effect of that force. So when you sketch an SD, you can't see forces. But when you sketch an FBD, it's like the mathematical structure of the whole problem. Okay? Yes, all forces shown. Again, all forces that are relevant. Like for example, did we need to show the gravitational attraction between the textbook and the moon? We know it's there, we know it's very small, we know it's very weak, but we know it's there, but yet we know we shouldn't show it because it's completely irrelevant. Good. Again, employ logic. Okay, what else? This one has motion information. Does that one also has motion information? Yeah. Yes, of course. Both you're allowed to put motion information. Okay. Just so you know, these are all the features of my SD. This one has a couple of more features. Number 4. Yes. Please do not make the forces point in. You make the forces point out. If you're doing an engineering analysis, you make them point in because it depends on actually pushing or pulling. But then when you do the analysis, you will actually assume they still point out of the of the system. But when you sketch them in an engineering course, you have to sketch them exactly according to what they call the action point. The action point. Okay. Okay, everyone, pencils down. Okay, let me prove to you that actually it matters how you push on an object. If I push, does it matter where I push on this table? What do you think? Is the motion of the table going to be affected depending on where I push? Yeah. Of course. If I want to make this table go straight forward, where should I push perfectly? Or where should I try to push perfectly? Exactly where you are. Wherever I assume that the center of mass is, and I push. How did it move? Straight forward or did it turn? What does that mean? Was I exactly at the center or offset? I was offset. Which means what? Wherever you push does make a what? Does make a difference. And that's what engineers care about. In a physics course, we don't. We always assume that everything boils down to a what? Does it matter where you push on a single point? Of course not, because a single point has no size. There you go. That's right. Finally, sorry. Okay, everyone, just so you know, in an FPD, you are not allowed. By the way, there's a small thing we're going to add here. No kinematic info. Okay, so you cannot show velocity or speed. You cannot show distance or displacement. You cannot show time. You can only show one thing. What's the only thing I left out? Say it. Acceleration. Everyone, the only thing, the only kinematic variable you can show on a what? Is only what? Acceleration. You will know why when we do Newton's laws of motion. So I want you to write here under this one, except acceleration. Go ahead. Except acceleration. You don't have to show it, but if you want to show something, you only show acceleration on the diagram. Okay? And you will see why when we start doing Newton's laws probably tomorrow. Okay? So except for acceleration. Anything else? Big no. You cannot show it on FBD. Okay. Finally, the disclaimer. I will violate these rules a little bit. How so? Whenever I sketch an FBD, I will never start by sketching an FBD. I will always start sketching what first? A system diagram, because I like to see the full visual of the problem and then focus on the single object of interest and then make all the forces come after it. Why? Because then I know why each force exists, because I know what other object pushes on the object of interest and gives it that force. Okay? I sketch a system diagram and then choose an object and put the forces on it. Again, this is my style. You want to go with it for the rest of the course? Please go ahead. You want to go with the official definition, which means you sketch nothing but a dot and everything coming out of it? Go ahead. I'm going to leave it up to you. Okay? All right. So here's an example of what? Here's an example of what I like to call 2-in-1. a system diagram with an FBD for the same problem. Like this. Okay. A box is sliding down an inclined ramp. By the way, get used to ramps because they are going to be in every single part of this course and in first year physics as well. Ramps are everywhere. Okay. Question. Sketch a free body diagram. Of the what? Yeah, I could have told you sketch an FBD of the ramp, but the ramp is not moving, so it's really of no interest to us. Okay. So what two objects are really important here? Like what two objects are mentioned in the statement of the problem? A box and a ramp. What's the easiest way to sketch a ramp? You already have it. How do you usually sketch a ramp? A triangle, usually a right angle triangle, but it doesn't matter the base as long as there's a hypotenuse. Okay. Well, the fact that I just said hypotenuse means it has to be a right triangle, but let's just let that slide. Very good. Okay. What's force number one? All right. So, sorry, you want to see the pencil? Very good. Okay, gravity. Okay, what's force number two? What reacts to gravity? Hint, there's a surface. Yes? No.
I have a question.
How many people have questions? Yeah, you should all have questions. Okay? I would love for everyone to ask the question, but let me just choose a spokesperson here. Kendra, what's your question? Or maybe you have two questions now. But at least you have one. Huh? Listen up, everyone. I made a mistake on purpose. And you have no idea how many people actually make that mistake, even up to first year physics. What's the mistake? Well, it is pointing down.
Straight down.
Could gravity ever point like that? Okay, why do you think so many people would actually think it points like this? Because we have a what? Okay, what's the proof that gravity could never point like that? Imagine if you vanish the ramp. Would the box ever move like this? No, seriously, think about it. The force effect is when you eliminate everything but one. So let's eliminate the ramp. How would the tablet move? This way or just straight down? You got it, exactly. Yes, it was a mistake on purpose. What's the other mistake? Josh.
The force, the normal
normal.
force is not perpendicular.
What does normal mean in math? No, perfectly. What does normal mean? Perpendicular. It only points up if the surface is what?
Up.
It's only vertical if the surface is what?
Horizontal.
If I tilt my surface, what happens to my force? It has to what? It has to tilt with it. So what's the correct direction for Fn now? It has to be perfectly what? 90 degrees to the what? To the surface. Is that making sense now? So always make sure you never fall into either of those traps. Gravity never points anywhere but what? Straight down towards the center of the planet. And normal is another word for what? Perpendicular. So you have to make it perpendicular. Solid. This is not perpendicular to that. That's not 90 degrees. That's an obtuse bigger than 98. Perfect. So, everyone, let's erase. Come on. There we go. 1 second. Erase. So, you sketch from the center. Come on. And from here. Oops. You go straight down. And that's FG. And well, 1 second.
I just
Josh, what's up?
So we have to show like the right angle.
No. Oh, everyone. No. Remember, everyone. When you sketch those, you're gonna sketch them mostly by hand. Rough diagram. You do not have to prove to me that this is the fact that you tilted it means you know it. You see what I mean?
But like, should we just like put the square just to like make sure that it is like you're saying that
Oh.
it is right?
Okay. When we actually do the big legit FBDs tomorrow, yes, that's what we're gonna do. Today, just showing you the direction. But Josh has a point. Josh is telling me, Shouldn't I show you that's actually 90 degrees to the surface? That's actually what we're gonna do tomorrow when we put the what? When we put the axes, the two axes, X and Y, on the system. Okay, what's force number 3? Applied. Which way? It's sliding down.
So down.
So which way is the applied force acting?
Down.
Okay. Is there friction on the system? If something is sliding down, how does friction act on it? With or against?
Bringing it up.
Never with, always against. So which way is what do you call it? Friction gonna act? Down the ramp or up the ramp? Okay, so you mean like this?
No.
How so then?
The friction.
Exactly. Friction is always what? Along the surface, which means exactly. Thank you. Perfectly parallel to the what? To the actual surface itself. Sorry, to the actual surface itself. Let me just make it as parallel as I can. There we go. By the way, how is it moving? Up or down?
No.
Yes, Josh, go ahead.
Is friction always gonna act like
Huh?
against motion? So like
Okay, can friction ever push the object faster?
No.
Which means, can it ever act with motion? Or is it always against motion?
so it's always,
That's it. Done.
so
Fraction is a stealing energy force, not a providing energy force. Which means it always has to go against your motion. Which is very evident by anything you push. It comes to a stop. Does that make sense? Good. What force am I still applied? And which way?
down the ramp.
On the ramp. There's no applied force. There's no applied force. Did I tell you that anything was pushing that object? No. What does this statement of the problem exactly say? A box is what? No, not moving.
Oh.
Sliding. Do you need to push something that's already sliding? Or is the tilt of the angle already enough? Do you see why not everything has to have what? When do you only put applied? When there's an explicit mention of what? Of a pushing or a pulling or an actual agent into the problem. Please, not everything that's moving needs a force what? I'll prove it to you. Everyone, look. Eyes on the board. Okay, everyone. Am I moving this eraser?
Yes.
Do you see me actually applying force?
Yeah.
All right. From the moment I left it, did I touch it?
No.
Yet was it moving?
Yes.
But was it under any applied force? There you do you see what? It was as I pushed it. But once I left it, was I actually actively acting on it with an applied force? But it was still in what? But what kind of motion? Speeding up or slowing down? Because decelerating because of what? Do you see what I mean here? Not everything in motion has to have what? Applied force on it as it's moving. Would it have had applied force on it before? Maybe. Most likely, because how did you get it to move if you didn't put applied force? Do you see what I mean here? Never put applied force unless you know something is actually what? Something is actually what? Being applied physically against the object. Okay? Please make sure read the problem carefully. Okay? Again, when you slide things, do you need to push the thing or just you need to tilt it just right? You just need to tilt it just right. I mean, okay. All right. Am I tilting? How come it's not moving? What's the force that stops anything from moving? Okay. Should I tilt less or more to get to move? Okay, why? Because when you tilt more, what force are you trying to bring more effect of? There you go. By the way, we will try to do an experiment where we decide what the magic angle. There we go. Does that make sense now? Did I physically push it or did I just let gravity take care of it? But I still had to help gravity by making a what to the system? I make a tilt or an angle. You guys. That's why ramps are very important in grade 12 physics. because of these situations. Awesome. All right. So again, when did we ever mention pushing? I didn't. You thought it existed, but it actually doesn't. So everyone, I actually want you to write applied force. Go ahead. I want you to write applied force and put an X through it because I want you to see that it's not problematic to have thought of it first, but now you know why you shouldn't have thought of it in the first place. Because there's no pushing explicitly mentioned. Okay? All right. Oh, that's motion. Okay, everyone, let's do quick FBDs. Come on. Well, you know my style now. There will be FBDs, but still mixed with what? With SDs. Okay. First one. Yeah. A pen sitting on the table. Is there any motion here? All right. So we have a lot of space, so let's do the first one here. So part A. So what objects should I sketch if I wanted a system diagram? Table. Thank you. Table. And then what? A pen. Everyone, in physics, anything can be sketched as a what? As a box. Just sketch a box. A car could be a box. A plane could be a box. A building could be a box. Just sketch a box. A person could be a box. Box. Okay. What's the first force for sure? Thank you. If it were only gravity, that pen would be falling down, free falling. But it's not. It's sitting idly on the table, which means there's gonna be a counter force.
Sir, do you want us to draw the mixed one or each?
It's completely up to you. What would be the official way of doing this? Not sketching a box, not sketching a surface, only sketching a what? A thick dot. Yeah, seriously. This is, by the way, I'm going to show you so many diagrams from the university textbook, and many of them will look like this. Just a dot with FG going down, look, and FM going.
Oh no, the question says draw both of them, like separately.
Oh, then I'm going to sketch both of them together.
Oh.
You see? Yeah. Again, this is a textbook question. My question is just going to be like sketch an FBD, and you decide if you're going to do it like this or like this. Is there any motion direction here? No, there isn't. Done. Full marks. That's it. Okay. Next one. A rope connected to a crane, raising a piano vertically, upward at a constant speed. Okay. What objects do we think are mentioned in the problem? Objects. A crane, a rope, a piano. Anything else? Nope. That's it. Done. All right. Okay. So. All right, a crane, here's my way of sketching a crane. This is the what? The rope or the cable or whatever you want to call it. Yeah, this is way too much space, I didn't need it. There we go. And a piano. How can I sketch a piano? Just sketch a what? A box. I'm gonna make it fancy. I'm gonna sketch a 3D box. Okay. And technically, it's connected to the piano right here. Ah, fancy. Okay. Which one of those three objects is the most interesting one? Well, they also did say sketch it of the piano. All right. What are the forces on the piano? First of all, is it on Earth?
It's on Earth, it's not connected to it.
No, but is it on the surface? Sorry, you're right. It's not physically touching the surface of the Earth, but is it still subject to the gravity of the Earth? Yeah. That's what I meant. Thank you. So obviously, force one is what? Gravity. So go ahead and just now. How do you sketch it here? I don't know. Just sketch an arrow coming out of it, maybe below here, like this. Like this.
Draw 3D.
Yes. Okay. What else is there? Who said tension? Why is there tension? Because what's physically connected to the piano? A rope. And the rope itself is under tension, but that tension is transferring to the what? To the hook of the piano. Exactly. So, what was the symbol for tension? You can either do FT or just what? Just capital T. Okay, so the tension, again, everyone listen up. This is important because many people are confused by this. Is the tension in the piano or in the rope? It's in the rope. But what is it acting on? Right here, everyone. Where is the tension? Is this under tension or is the rope under tension? The rope. But the tension in the rope is helping what? Lift the what? Lift the tablet. So it's like an applied force. Do you see what I mean? You do not have to call it applied force, even though it is being applied to the hook right here. We just call it what? Tension, because it is technically transferring to the tablet. Okay, it's very important. Any normal force here? Normal. What if the piano was not being pulled up? What if it was being lifted on a platform? Then would there be normal? Yes, you see, it depends on what the problem says. All right, so there's no normal. Is there any applied other than those? Is there any friction on this? Well, okay, technically, air drag. Did the question say anything about eliminating air drag? They didn't. Okay, everyone, if this is moving up, how does the air drag act on it? With it or against it? Yeah, how many people know skydiving? When someone jumps off a plane and they go down, is the air pushing them down or is it pushing them up? And that's big. And you know how they slow? Does anyone know how they slow themselves down or speed themselves up? Exactly. Surface area, right? If you want to produce more drag, what do you do? Do you go like this or do you go like this?
That's not what they flaps.
Say it.
They have the flaps.
Yes, exactly. But also they also what? They increase the surface area, which means they increase the what? The exposure. So to slow down, what do? You go into the eagle pose, right? To actually slow down, what happens? What do? You tuck in. Why? When you tuck in, what happens to your surface area of exposure? Does it increase or decrease? Which means what? You become like a what? Like an actual just small sphere, just going through the what? The medium. Make sense? So that's why. So technically, there is air drag, and since the motion, which way is it moving, by the way? Is the crane lowering it down or raising it up? Okay, so the motion is going up. The motion, come on. The motion is going up, which means air drag technically, you want to sketch it like this, force of drag. Done. That's it. Okay, who would like to read question C? This was A and B. Who would like to say question C? Nora, go ahead. A lamp has what? Just begun. Everyone, look. It's like this. Everyone here, eyes on me. Right here. If it just began falling, is it touching the table? So is it under normal force or no more? You got it. Okay. So it's okay. Is there still contact between this and the table? Once it begins falling, is it touching the table anymore? No. It's purely in what? Free fall. You got it. So sorry. New. Okay, so I guess I'm gonna sketch a corner of a table. I'm gonna sketch the lamp kind of like tilted. I shouldn't make it touch. Yes. Here's a lamp. What force is on it for sure? What's making it fall? Gravity. So choose a point kind of like to represent the center of it and just go down. Any normal force on it now? No. But on purpose, we did not make it touch. Any tension? Is it connected to any ropes or cables or chains? Nope. Any Any applied? No, it's not. It's falling now. You don't need to add, you don't need to assist it anymore. It's falling. How about air drag? Okay, hold on. Has it been falling or did it just start falling? Okay, everyone, eyes on me. What force is this eraser under? What forces?
Normal.
Gravity and?
Normal.
Oh, it would be normal if I hold it like this. You see what I mean? I always want you to think of normal if there's a surface. But how about if I do it like this? Is it really normal or more like applied? Applied. I'm applying a force, right? Any other forces? Any friction? Okay, let go. As it was falling, did gravity ever go away? No, so gravity is still there. How about my applied force? Is it gone now? Yeah, there's no more physical contact. How about air drag? It's what? It's swooshing this way, right? Okay, but when you just let go, has air drag started to act on it yet? Which means technically here, is air drag in effect or not yet? You got it, that's it. Remember, air drag requires motion through the medium. Has it started moving, sorry, has it been moving through the medium yet? Is it starting to? Which means still no air drag, okay? Air drag needs what? Needs motion to have been for a while. Thank you. All right, so that's it. That's the only force on this. Jinan, what's part D? Last one.
A dresser that is being pulled to the right of the ramp into a delivery truck by a cable paired with the ramp. The ramp is at an angle of 14 degrees above the horizontal.
Okay, quite a few things. Yes, hello?
Good morning.
Good morning, yes?
Would you be able to send kind of the jar of guidance whenever?
Sure, no problem.
Thank you.
Yo. Okay, what objects do we have? Come on, system diagram. A dresser, which is literally a box, a big box you put stuff in. Being pulled to the right, up a ramp, two objects. Into the bed of a delivery truck, not the whole truck, at least just the back part. By a cable, so there is what definitely? Tension. Parallel to the ramp is angle 14. All right, let's do this. So, okay, I'm just gonna use some grid lines to help me out. Okay, ground, tire, truck bed. Sorry. Go ahead, come on, sketch. Ramp. Dresser. What's the dresser connected to actually pull it? A rope, or they said a cable. So, now do you think the cable looks like this?
No.
No. How does the cable look like? Most likely, it's parallel to the what? Parallel to the ramp. All right. Although you can definitely pull like that. Okay. Which one is the most important object here? The dresser. Okay. Force number one. Gravity. Which way exactly? Straight down, no angles. Straight down, no angles. All right. So from here, you go straight down, as straight down as you can. Yep, that's decent. What reacts to gravity? By the way, do you see how I always do them? I do them in pairs. I always do it in cause pair, effect pair. Cause, effect. Fg happens first, Fn reacts. Which way does Fn go?
No.
Normal, which straight up,
No.
tilted a little bit. So maybe like this. Sure. All right. What's in the cable? Tension. We can sketch it like that if you like. Oh, not bad. Sorry.
Shouldn't it go the direction of the cable?
Yeah.
Oh.
Yep. You're right. Now, obviously, you can make it come out of the center of the dresser. It's all that when vectors happen, it's not going to matter where you place the vector. It matters what's the direction of the vector. Okay. What else?
Friction.
Are we told that this ramp is perfectly smooth? No, you're not. Even so, you're not even told neglect friction. So you have to assume it exists. Where does it exist? Down. So that means feel free to point it this way. I like to give it a physical feel. I like to point it where it really happens. I picked this up after like touring, the first year engineering statics for a while. And I was like, you know what? I think we should put it exactly where it actually happens on the diagram.
That is supposed to be from the center.
What's up? Sure.
Yeah.
Any other forces? No. Any applied forces? No. Technically, the only applied force is tension, but we have a name for it. It's called tension. Yes, Mohammed. Sorry. Okay. Which way is it moving? Which way is the dresser end up moving? Straight up. So that means the motion somewhere here. And friction is always against motion. Make sense? Always. Which is actually, you know what? Ahmed just gave us a good idea. Sketch motion first and then decide which way friction points.